Welcome everybody to the second talk of the SNAPP Fall 2025 season. Today we're delighted to have Florin Ciucu from the University of Warwick. Florin is an expert on queuing systems and stochastic models for computer systems and communication networks more generally. And he's the winner of the IFIP Performance Best Paper Award, and he's the author of some recent work on new bounds and queuing systems that I find really exciting. And he's going to tell us about some of that work today. So please, Florin, take it away.
Thank you, Ziv. So I kept telling Ziv that I'm not a queuing theorist, and yet I come to talk about queuing theory. So before you challenge me, I have to admit that I don't know what ultra sharp means in the context of the title. So more appropriate title would be on some subjectively ultra sharp bounds in queuing systems. So the goal of the talk is to introduce two classes of these subjective ultra sharp bounds, one in single queues and the other one in tandem queues. Okay, so in the barest form, the queuing problem is essentially about having a sequence of or flow of jobs with some random inter-arrival times and service times at some servers. And the actual problem that we care about is to express the tail probability for the queue size or for the waiting time in terms of a nice function, which should reflect the properties of the arrival process or the capacity. And in the case when we schedule multiple flows of jobs, we'd like to see, in a way, the characteristics of the scheduling inside that function f. So that's the problem we care about. Now, despite its simplicity, queuing theory evolved as one of the most successful branches of applied probability. And I'll only mention that the queuing problem, in particular this computing the tail of the queue size, is exactly the same problem as computing the ruin probability in financial analysis. So instead of queues, one and inter-arrival time, service times, one would deal with premium sizes and claim sizes. But mathematically, they are the same problem. Now, speaking of this concrete problem, we want a nice function f. So the problem is fairly easy to solve for the MM1 queues and intermediately easy to solve for GM1 queues. Now, once we forego this assumption of exponential service times, the problem gets quite difficult. So even that's my favorite example, the MD1 queue. Now we have an exact expression for the waiting time, the tail of the waiting time. So that's an exact expression. And I should warn any computer scientist who would try to solve this using a for loop that will run into severe numerical issues because these prefactors here, they are alternating and very large. So one would need numerical algorithms. Now, of course, in the GI-G1 case, the problem gets even more difficult as we don't have closed form expressions. One would need numerical inversions, and that's the renewal case. If we move to the non-renewal case, where we have some memory inside the arrival process. So here are some classical examples. This would be a Markov modulated on-off process. So two states, constant rate P. Here we'll have a Markov modulated Poisson process. So in each state, there will be Poisson processes producing packets or jobs. And on the right, we have even a more complicated Markov arrival process. Now, so solutions, they do exist, but again, there are severe computational issues when we multiplex many of these sources, and let alone in the case of scheduling. Now, about these non-renewal processes, I have to go back in history now. So the late 70s, 80s, and the 90s, so that was in a way the golden age of studying these processes, mainly because of the advent of voice and video in the internet. And a very fashionable technique at the time was effective bandwidth. And now moving to the 90s, I'm going to show my favorite plot from the 90s. So here, essentially, the authors, they took 60 Markov modulated Poisson processes, and they plot on the logarithmic scale the tail probability for the Q size as a function of the buffer size. In the middle, we have the exact result. On this upper line, that would be this effective bandwidth approximation, yeah, so which is actually, it's exact logarithmically and asymptotically. And then there are several other approximations in the paper, and there is even the Poisson approximation right here on the left. Yeah, so if we approximate the 60 MMPPs by just one Poisson process. Now, because I work for a major telecom provider, so I'm very good at reverse engineering this. So let's say that we ask the following question now. So assuming that we are given some QS, the probability of violating the tail would be 10 to minus 3 or minus 6. And then we have some fixed capacity for the network. The question is, how many of these flows could we admit, yeah, to satisfy this QS? Now, according to the exact result, so we can admit exactly 24, yeah. Now, based on a peak rate admission control, we can only admit 7. Based on the effective bandwidth approximation, we can admit only 12. And at the other extreme, based on the Poisson approximation, we can admit 78 flows, of course, at the expense of meeting no QS. So obviously, the effective bandwidth is just an over approximate, or if the network provider would employ this formula, the network would be underutilized. Now, the same authors conjecture that the actual tail probability for the Q, it's asymptotically, it's exact. So the theta, it's the asymptotic exact decay rate. However, the prefactor is exponential in the number of flows, which obviously this effective bandwidth approximation doesn't capture that. Yeah, so that's pretty much, because it cannot capture that, it's pretty much game over for the effective bandwidth. And in a way, from what I see it, historically, it was really game over for this effective bandwidth literature. At least there are very, very few papers after that. It wasn't game over for the Poisson approximation, though, which again would result into an overutilization of the network at the expense, of course, of the customers, as there will be no QS. Now, mathematically, the reason why effective bandwidth doesn't work to capture this prefactor is that it's unable to take into account the memory into the arrival process. And a natural, now random process to account for this memory in the arrival process is the martingale. So now I'm going to show some bounds from about 10 years ago. So these were done with my former student, Felix. And if you believe in supernatural, that's not the Felix Polacek that you know, it's the Felix Polacek, my PhD student, my former PhD student. So here we showed we are in a scheduling context now, in a setting. We have like two streams of Markov modulated Poisson processes and EDF scheduling with deadlines 10 and 1, I believe. That's why there is the band here. We have and then we plot we plot the tail of the delay again on the logarithmic scale. We have the simulations here, like in red we have the effective bandwidth result, and then we have the martingale results in green. Now, seemingly these are ultra sharp bounds, but they are not. And to see why not, so first of all, the utilization here is 0.9, which is something which was known from the people doing martingale bounds. So at high utilizations, yeah, so in heavy traffic, the martingale bounds are quite tight. However, if we move from, let's say, from 99 utilization to 75, the martingale bounds are not so tight anymore. So not so ultra sharp. Moreover, we extended the martingale bounds to semi-Markovian arrivals. Now, again, on the logarithmic scale, we see that the true results, they are not exponential on the logarithmic, on the log scale. Yeah, so we don't have a line, yeah, that there is a bend, you know, like at the beginning. So just using the simple exponential is just impossible to to derive these ultra-sharp bounds. And now the goal is to show how to do this, to get these ultra-sharp bounds, now again with the martingale techniques. And in order to do that, let me just quickly go over the main idea of Kingman from the 60s. So we have a single queue now. We have an arrival process. The service times are xi's. N of t is the number of arrivals by time t. A of t would be the compound arrival process. The queue size would be just the supremum of a random walk now with negative drift. And now we are going to fix sigma, so that will be for the tail. And now we are going to define t as the first time when this process exceeds sigma, this random walk with negative drift. Now, obviously, t is a random time. And so the main idea behind the martingale bounds is to rely on the following analogy. So the event that the queue size exceeds sigma, it's exactly the event that this random time, which is a stopping time, is finite. Now, quickly about stopping time. So for just some random processes, stopping time, yeah, it's a random time such that this event depends on the x1, xn only. Yeah, the classical example of first passage heating time. The one annoyance is that these stopping times can be infinite with positive probabilities. So the typical example, we have a asymmetric random walk, and if we take n the first time when the random walk hits 1, yeah, so this can be infinite with positive probability. Moreover, the stopping times, they are very misleading, at least they were to me at one point. So if we take an ID process, so we know by definition, yeah, so in expectation, the E of xn is just E of x1 for all n. However, that's not true for if we stop the process as a random time. And just the classical example, if we stop the process at, like when xn is exactly 1, then xn is just 1. So in expectation, it doesn't hold. Now, the reason this doesn't hold is that a stopping time, in a way, encompasses the memory of the process, whereas the process itself has no memory because it's ID. Now, the random process that naturally accounts for memory in the process is a martingale. So martingale, again, it's just a random process which has integrable. And then the key property is that the conditional expected increment is 0. So one can think of xn as the typical example of modeling the wealth of someone playing at the casino. Yeah, so if the casino is fair, then, like we'll deal with a martingale. Not everything is a martingale. So as I mentioned, an ID sequence is not a martingale unless the sequence is constant. Also, similarly, a Markov process, so one would need some kind of a transform of a process to get a martingale. Now, the crucial property of the martingale is the optional stopping theorem. That is, now we can actually stop the martingale at a stopping time, and then we recover E of x1. Yeah, so that's the simplest condition when n is bounded, so that's true, and there are like a few generalizations of this. Yeah, so this is just a counterexample. Now, very interestingly, this property also holds in the other way around. That is, like if we have a random process such that E of xn is E of x1 for all bounded stopping times, then the process is a martingale. Okay, now let's go to the Kingman bounds for the GI-G1 queue from the 60s. So now we have the TNs are the inter-arrival times, service times that's n. We have the drift, which is negative. So that's the waiting time now, which was the supremum of this random walk. Now we recall the analogy between this tail and the stopping time being finite. And now we need to construct a martingale from Tn and Sn. So we are going to construct this exponential martingale. So again, x would be the drift, and that's the exponential martingale, and theta can be chosen. Yeah, so theta does exist when the service times are when they are light tail. So theta, it can be shown that theta does exist. And then once we have the martingale, we are going to stop it at this stopping time t. But now, because t can be infinite with positive probability, we have to stop it. We have to take a deterministic time n, and we are going to stop the martingale now at time t, the minimum between t and n. And then we take a limit in the little n. Yeah, so now if we split this m at this time, yeah, so this will be the indicator functions, it can be shown that in the limit n goes to infinity, the second term vanishes. So now again, in the limit, we have the equality. At this point, we just replace m of t by the exponential, yeah, like just its expression. And at this point, so what happens is that these two terms, the exponential and the indicator, they depend on each other, yeah, like statistically. So we are going to take a very crude approximation. That is, we know that at time t, x1 plus xt is greater than sigma. So now I have a deterministic term that we just take it outside. And that's the Kingman bound. Yeah, and then in the end, we take n to infinity. Now, let's go a little bit more into it, into what's going on. So I mentioned that at the last step, we just replaced this random term, which depends on the indicator, by a deterministic quantity. And that's quite harsh. And that's the reason why these martingale bounds, they are not so ultra sharp if you want low utilizations. So now the way that we are going to circumvent this problem, what the main problem in a way is this indicator, which can be positive with probability 1. Yeah. So and now, in a way to get rid of this annoying indicator function, we are going to essentially construct, or we are going to compute these expectations under a new space or probability measure, under which the corresponding the stopping time t would be finite with probability 1. Yeah, so we can just safely remove this indicator. Now, we'll do that by forcing a positive drift in the process. So now I have, because I'm a computer scientist, and I always find it very difficult to understand change of measure, I have to give you the computer science view of to understand this idea of change of measure, which is quite elementary, but it's quite deep. So if we take x as a standard normal, and if we take x, the little x as 10, the question is, how much is the tail here? And that tail is actually 10 to minus 24. Now, a mathematician would be able to compute the integral. A computer scientist, however, will just run Monte Carlo simulations. Yeah, so like a for loop, and then we'll generate this standard normals, and then we'll try to estimate the little p by doing a very long for loop. However, a statistician would immediately say that, wait a second, this estimator has a very large relative error. Nevertheless, the computer scientist still wants to apply this idea, yeah, like of generating random variables and, like computing these indicators. And that's pretty much the idea here now. But now, instead of generating x's now, according to the standard normal 0, 1, we are going to generate different y's now. We're going to generate different y's. We're going to take these indicators, but of course, there has to be some weights associated to that. But the idea of the Monte Carlo simulation will be the same. And then now, again, to innovate, like so that the statistician will be content, we hope in a way for a lower variance of this, like of this term. Now, really what happens, so if we take h as a random function of x, and if we want to compute the expected value of this random function, yeah, so x would have the density f really. We want to re-express this expectation in terms of a new probability space, where we'll generate y instead of x. So really, like this expectation is just this integral. And now, if we really want to generate y now with a density g, yeah, so essentially we are going to replace this f of t by gt and then this fraction. And that's really that weight there. L of t is just the fraction, the f divided by g. This will be the densities. And now one can take y as the normal now centered in x with standard deviation 1, and then it's just and then one can actually do the Monte Carlo simulations. And now the idea is that now we'll have like half of these values would be roughly 1. Yeah. Okay, so now going back to our problem, so we want to force the positive drift to make that stopping time finite. So if we take x, so this would be the drifts Sn minus Tn. This would be the natural filtration. F is the limit of that. Pn would be the restriction of P on this Fn. That's the moment generating function for some theta greater than 0. And now we're going to define for each n, we are going to define these probability measures depending on theta and n, which is essentially we're going to have this exponential transform and then this psi of theta, so that's just the MGF of 1. Now this prefactor of the indicator, this is nothing else by the Radon-Nikodym derivative of Pn theta with respect to Pn. And we know from the Kolmogorov's extension theorem that on the big theta f, there is a p theta such that Pn theta would be the restriction of p theta on Fn. So these are just some technical details. Okay, now again, keep in mind our goal is to force that positive drift. Now, if we look at this MGF, so we know that the MGF would be at 0 and the theta is 1. We know that it is convex. Therefore, at theta, the derivative of psi it's positive, but the derivative of psi it's nothing else but the expected value of x under this new measure theta on Pn theta. Yeah, so therefore the drift now x is positive under this new measure. Yeah, so on the new space, t is just finite with probability 1. So now to get to our Q now, so we're going to use the Waltz fundamental identity, which essentially says like for a positive random variable y and any stopping time, then we can express the expected value under theta of y with this indicator in terms of the expectation on the original space. And now as we have the freedom to take y as we want, we just take y as just as this negative exponential. And then we can now compute the expected value of, yeah, so this is actually the probability that the waiting time is greater than sigma, what we actually wanted. We express that on the new space in terms of this indicator function now, which now becomes 1 on the new space. And we're still left with x1 plus xt, which would be sigma plus the overshoot. And this was known, yeah, so this is nothing new here. This was just known. And now what people did, they tried to express this overshoot. However, that's very difficult to express the overshoot, especially non-asymptotically. So now our idea was really very simple. So essentially we express the overshoot or the tail of the overshoot as really, so R sigma, which would be the overshoot by how much we exceed sigma. So we'd exceed x. So this event is nothing else that there will be an n such that, you know, like up to n minus 1, we do not hit sigma. And then at time n, we exceed, not only we exceed sigma, but we beat this additional x. And this is it. And that's essentially what we used. And then we use like a few other like little tricks. And based on that, we managed to get an exact result now on the tail of the waiting time. And that's just the classical exponential if you want. And now we have 1 minus this series of terms. Now, this is, I have to say that this is not an analytic series. Nevertheless, we can express them recursively. So Gn, we can express Gn as a function of Gn minus 1. Now, let me go to my favorite example, the MD1Q now. So we have the arrival rate lambda, service time would be constant S. So the theta that we need for the exponential, so that's Yeah, so we have to solve this numerically. And now, essentially, we are going to compute these GNs. Yeah, so G1, G2, G3 can be computed using elementary integration, like really like high school integration now. And using the first term, if we are lazy, if we only do one term, then we get this bound. And if we compute two terms, we get this other bound. And we can compute another one and so on. This would be the Ross bound, which is essentially the slightly improved version of Kingman's martingale bound. And then here we have the exact result. Okay, so numerically now what do we have here? So we look at the tail of the waiting time on the logarithmic scale. And now at the bottom in pink, we have the simulations. So we have this waving effect because S is just 5. That's we have 5 here. Now we have the Ross bound, which is up there. So it's very important to note that now we look at 10% utilization. Yeah, so the Ross or the Kingman bound, these are like roughly one order of magnitudes apart from simulations. And now with only one term in the really lazy scenario, we'll have the blue curve, and with two terms, we'll get the green curve. Yeah, so that's in a way what I mean now by ultra sharp. Now the point is that the G1 and G2, the big gains happened right at G1 and G2 and G3 and so on because of that positive drift that we managed to get. Now quickly, let's go to non-renewals. So here we have the simple Markov on-off process, alpha, beta. So these are the discrete time case. So this would be probabilities. And now we have two scenarios concerning this Markov on-off processes. We have the more bursted and Poisson case, in which the transition probabilities, yeah, so they are in a way like they are quite slow, so it takes a while to change. So that's the more bursted and Poisson case. And at the other extreme, when the change is much frequent, that would be less bursted than Poisson. The fundamental difference is that the results now they are or the prefactor is exponential in n. However, the actual gamma is less than 1 for more bursty and greater or equal than 1 for less bursty. So fundamentally, these are very different behaviors. So now to get the exact result, I won't go over this. So I'm just so this will be essentially this bound now. So up to here, this will be the martingale bound. So essentially, we have the theta h. This would come from the eigenvalue eigenvector problem, and then the g case we can express them in closed form. They depend on this transition probabilities and the h's and so on, and even the sum has to be taken very carefully depending on the utilization. And by the way, we have here like NL sources of each type. So we look at more bursty and less bursty. So we have N1 and N2. So numerically now, so here we look for the more bursty case. And then at the bottom, essentially, we have the simulations. And then in red, we have the Kingman results. And then we have, depending on how many of those G's we can actually compute. Yeah, so we see that with 5 terms, we get very, very close to the simulations. Same in the less bursty case. There we don't have to struggle so much. Just the 3 terms we pretty. And by the way, I mean here we are already like a 10 to minus, I know like 8, where essentially where I stop the simulations. And finally, here we are in the case where we multiply 2 sources, so more bursty and less bursty. And again, with 4 terms, we get to the actual simulations. Now, what's to be noted from here is that the true behavior of the tail is very complicated. Yeah, so that's really the true behavior of the tail. So in a way, looking for exceedingly nice expressions, it seems like a very daunting task. Yeah, so that's why the way that we deal with it is to have these G's that, yes, they do have a quite complicated expression, but all these expressions are in closed form. Okay, so that brings me to the first part of the talk, to the end of the first part. So now for the second part, we'll move to the multi-node or the queuing network case, and in particular, the tandem queue case now. So now, again, we want to derive ultra sharp, if you want, end-to-end results. And in particular, we want to derive some ultra sharp bounds on the tail of the sojourn times. Now here I'll just mention that the problem is very difficult. Yeah, so it's a tandem network case of two MM1 queues. So just some terminology. So the waiting time is essentially how much time we wait, and the sojourn time would be waiting plus service. Now we know that the local sojourn times are independent. However, the local waiting times are not, which may be counterintuitive. Now the way to see that, so one can see that from so that's from the it's Burke's proof. Yeah, so that's a classical proof. So essentially, if we look at the waiting time of the same job at the two queues, yeah, so this would be the waiting time of the second queue. However, the conditional waiting time of the second the waiting time of the job of the second queue is 0, conditional that it's 0 at the first queue. That would be strictly greater than the probability that the sojourn time is 0 at the second queue. Now, the reason I'm doing this is that I can re-express these waiting times instead in terms of this n of 2. So this would be the number of arrivals by time x plus y. So x would be the arrival time of the job, and y would be the service time. So now the point here is that n1 and n2, they are not independent at different times, let alone at random times. And that's unlike the product for formula, where we take n1 and n2, n3, and so on at the same time. Yeah, so now to deal with end-to-end results, so end-to-end sojourn times, in a way we have to deal with the number of jobs at different times at the queues. So the goal here is to derive end-to-end results on the sojourn times for non-Poisson arrivals, and however, we can only manage to address the case of light tail service times. Now, what we know from the literature is essentially it's the correspondent of the effective bandwidth result for one queue. So now we have the effective bandwidth result for multiple queues. So what we have this exact logarithmic asymptotic result, which essentially gives us the true direction of the tail of the sojourn time. But it's just the direction. We do not have the prefactor. And the goal here, yeah, so we know that, again, we know that this is an exact result. So that's a big theta, this exponential. However, what we want the prefactor and any other additional term as enclosed form, and for non-Poisson arrivals, and finite x. So I'm going to only present the results for two queues. We have the more general result for n queues. So just some terminology here. So now we're going to look at a system with n jobs. So n denotes the number of jobs, and k would denote a generic job. Now this x's are the inter-arrival times between jobs, and the y service times Q1, z's service times at Q2. So if we replace k by n, we see that job n arrives x3 after job n minus 1, and service times y2 and z1. And we do this for a very good reason, even if many reviewers, they hated us for this notation. Now, to express the sojourn time, we do nothing fancy. Yeah, we just do the standard Lindley's equations. So we look now. I introduce now the upper script. So the upper script would denote the queue size. So tau, the departure time or the exit time at Q2, of job k plus 1 can be expressed in terms of, like the previous departure time and the arrival time from, or the departure time at the previous queue. Yeah, so nothing fancy. And then we can express the exit time of job n. So that would be like a double supremum involving, of course, the inter-arrival times and the service times of the queues. And that would be the sojourn time of job n, so the exit time minus the arrival time in the system. So now we can re-express the sojourn time in the limit n. So we're going to take n into the limit, and we're going to express the sojourn time as the supremum of two random walks plus that one would be the service time of job n at the second node. So what we have here, so the first random walk, so this, if you just ignore the yk, the service time, this is just the standard random walk for one queue. Yeah, so UKs would be the drifts at Q1, whereas the second random walk, so this would be that would involve the drifts now at the second queues, the V's, and at the first queue. And then we have to take a double supremum. And there are some nice recursions about these random walks. Nevertheless, these two random walks now are very unintuitive, especially for a queuing theorist. And we were shown from a very nice reviewer a very good interpretation of these random walks. So the first one, again, is nothing else but the sojourn time of job n at the first queue. Yeah, so it's nothing fancy about it. However, the second one, yeah, so here is just an example where we have Q1, Q2. This would be the time axis, n minus 1. So that's when job n minus 1 arrives at the first queue. And that's when it, and then that's when it will depart the second queue. And that's job n. And again, right here arrives at the second queue. So the second random walk is essentially T22. It's the exit time of job n minus 1. Yeah, it's essentially this quantity here. The exit time of n minus 1 minus the arrival time at job n at the second queue, which may be, I'm very sure that it's intuitive for a queuing theorist. It's not intuitive for me, but it's a very nice interpretation nevertheless. Okay, now here is the main result. So recall that our idea was to express the sojourn time as the maximum of these two random walks. Now, if we take the joint distribution of these two random walks now, that's the psi. Now, this joint distribution is the unique solution of the following integral fixed point equation. Now, the symbol is the minimum. The u, again, the u would be the drift at the first queue. V would be the drift at the second queue. So again, this is the unique solution of the integral fixed point equation on this compact space. So that's the psi. And now what can we do with it? Essentially, we can very easily compute now bounds. So that's the main result. So now we know from the analysis of the G1 queue that it's very difficult to solve these equations, these fixed point equations. And now, as we know that, we are not going to solve an equation, we are going to solve an inequation. Yeah? So we are going to relax now the equality into an inequality. So if we somehow manage to find the gamma now, where again, essentially we'll be solving an inequality and not the equality, then we'll know that that gamma would be strictly or less or equal than the psi that we cannot find. But that gamma will give us immediately close for bounds now on the sojourn time. So again, this is the end-to-end sojourn time. Yeah, so that can be expressed as the expected value of gamma taking the z would be the service time of at the second queue. Okay, now about the structure of these bounds now. First of all, So again, keep in mind that we know how to get the exact asymptotic result now, and the key is to get the prefactor. And the prefactor, we, in a way, even from the bounds on the GI-G1Q, we know that they have to have a polynomial structure. And that's pretty much what we want to get here. So now essentially we want to solve this inequation now. And now we're going to show that this gamma, it has a polynomial structure. So we are now in the general non-homogeneous case where the service times can, can have different rates at the both Q's. And now we have the theta, so that's the standard theta even from the 1Q analysis. And now the theta 2, now we have to account for both of these drifts now, but nevertheless, if the service times are light tail, theta 2 can be shown to exist. And now one can construct these indicator functions depending, essentially it depends on these thetas. Now there is some other technicality here. Now the main result is that there will exist a polynomial or a constant P1 and a polynomial P2 of two variables, U and V, such that gamma will have this structure. Yeah, so now we managed to get gamma in terms of an polynomial, to have a polynomial exponential structure. So now there are two exponentials in theta 1 and theta 2, which should make sense because we have two Q's with potentially different service rates. And then now we have one polynomial now for only one Q for the first one, and then the P2, it has somehow to account for both of these Q's. And if we also think about the Erlang distribution in the MM1, even in the Jackson network with equal service rates, the Erlang distribution, there is a polynomial structure for the prefactor. Now, to just give a few more insights about this polynomial structure now, so let's look at the bottleneck. So now the first case will be when the first Q will be the bottleneck, so the service time here is larger than expectation at the second Q. And now what happens is that both the theta 1 will equal theta 2. Yeah, so in a way, the system now is dominated by the first Q. And then that's the indicator function, and then the degree of the polynomial, the P2, which is seemingly supposed to be a polynomial, like a true polynomial, is just 0. Yeah, so the structure of gamma now will just essentially be two exponentials, the theta 1 and theta 2 are equal. Yeah, so here is just some constant and an exponential because the system is dominated by the first Q. However, in the second case, when Q2 is the bottleneck now, and under an additional condition that Y now, the service time at the first Q is not thin tail, concretely, it's not, let's say, it's not Gaussian, then it can be shown now that truly now the theta 2 or the second Q truly dominates the system. Yeah, so the theta 2 is strictly less than theta 1. The degree of P2 now will be 1. And gamma, the structure of gamma now, will essentially be dominated now by this polynomial, and then we have the exponential in theta 2. Okay, now let me derive now closed form results now. So now we know that we have to look for these gamma functions, which has this structure. So we know that from the previous existence theorem. And then essentially we have to find these constants A, B, C, D. And we are going to do this in the GM1 case. Yeah, so the service times are exponential. They are equal at both Q's, but the interarrival times are general. So again, this is our integral inequality. Yeah, we have to find this A, B, C, D. And now our strategy is essentially to break this down into multiple inequalities to make it easy for us. So now we have the following set of 5 inequalities, which are sufficient. Yeah, so if we manage to find A, B, C, D satisfying this, then this would suffice for what we wanted to get. And again, this case can be computed from the so they depend. Arc would be one of these drifts here. Yeah, so it's either the first or the second one. Okay, now, so solving this, so for the GM1 M1 case, we're able to compute this in closed form. And here will be the result now on the sojourn time, again, over 2 Qs. So what we have, so we have 2 branches essentially, depending on this alpha. So alpha depends on the interarrival process, and beta also about the service process. That's the theta that we get. So that would be the standard theta that we get even in the single Q. And what's to mention, it's this polynomial structure, which somehow it creeps in on both of these branches. That's the tail for the waiting time, which is significantly more complicated than sojourn time, and you'll see why. Now, if we compute this for the MM1 case that we already know, so for the MM1 case, we are actually able to recover the exact result. So that's the Erlang distribution for the sojourn time, and that would be the distribution for the waiting time, which again is seemingly more complicated. And this was obtained sometime in the 70s or 80s, from what I can recall. Okay, so now we're going to compare this bounds for the GM1Q against essentially large deviation results. And this would be the simulations in the DM1 M1 case and in the Erlang 2 M1 case. So the bottom, we have the simulations. In blue, we have our bounds. And now we have the bounds of multiple utilizations from 0.5 to 0.95. And on top, we have the, so this would be the large deviation bounds. Of course, these are not mathematically correct in a way because we just exceed 1, but this would be just bounds on the tails. And this would be the corresponding bounds now for the Erlang 2 case. So again, and we did a lot of experiments, and in all of these cases, we managed to get for the bounds, they are just very, very sharp. And the reason for that was essentially the amount of work we put into solving for this. Well, first of all, to break down this inequality into 5 inequalities. And then, of course, we had to break down or to solve this individually for the GM. And of course, the M was instrumental somehow that we managed to get these nice expressions. And so if I can just mention, well, I didn't mention that the large deviation result is essentially based on the Boole's inequality. Like to break down, like to compute the supremum of a random walk, one would need to apply the union bound repeatedly and so on, and that simply does not capture the memory in the arrival and then in what's going on actually in this random walk. Expressing the Q is seemingly it has memory, and the union bound is just simply unable to account for that. And so that brings me to the conclusions. So hopefully, yes, I could show that these bounds are not, yes, they are seemingly subjectively ultra sharp. In the single node case, they can be made, the bounds can be made arbitrarily sharp, depending on the amount of effort one puts to solve elementary integrals. Whereas in part 2, yes, in these cases, they are ultra sharp. However, once we move to different service time distributions, they are not ultra sharp anymore, simply because one would need a better way to deal with this integral inequality. And that's it. If you have questions.
Let's thank Florin for a great talk. So yeah, there's time for some questions. So does anyone want to get us started with questions? Okay, I have a question. So if we this is about part one. So you had this recursion for the for the G functions.
Yep.
Okay. And you said that basically that these G functions were yeah. So
Sorry.
yeah,
Yes.
yeah, this is good. Um, okay. So is that so basically so I understand that these G fun so basically what can you explain how or is there some intuition for what each GN represents? Is it like the
Uh,
overshoot if we overshoot on time n or something? Or something like
okay,
that?
so the main so what's going to break the problem here is essentially to get a good structure or to understand what's the true structure of G1
Okay.
or to understand what's the true structure of all of them. And then one can parameterize that, and then one can immediately, or computational will be very easy to compute all the G's. Otherwise, one would have to struggle doing these integrations. I mean, I struggle for MD1. I struggle in the sense that I had to spend, like an hour or two for like two
Yeah,
terms because it's quite tedious. But if one is able to understand the structure of G1 and Gn in general, then it's very easy. Yeah, so computationally, and of course, one can compute the sum and then can get like a nice structure in there. But these indicators are very annoying. Yeah, so you see that they are all subject to these indicator
mhm,
functions. They now you have to break the integral into two, and then it just gets very tedious. And that's what we are unable to do to understand truly what the structure of the G.
I see. Is there so so first okay, so my first question was just about the sort of what GN means, but I think just staring at this answered that. But then so what you just said, so if you drop is there some you said okay, the indicators cause trouble. Could you drop the indicators and get a bound? I guess it would be in the other direction, but would that sort of lead to a useful bound?
I don't know. I believe these are essential, these indicators.
Mhm.
Again,
Okay.
the goal is to keep it exact. I mean, honestly, that's my,
Oh yeah, yeah.
but that would be too much to ask for. But once one is able to understand the structure of the G, I mean, yes, I mean, you see that it's two exponentials, like would be the overshoot. I mean, we know that T happens at N, yeah. So, um, and then it's just there. It's this, yes, just the overshoot, but on two exponentials. And then, yeah, in principle, one should be able to get a nice exact result, or at least computationally, because if one makes n 10, I mean, it's pretty much enough for everything. Uh, because again, because of these positive drifts, the gains happen right away on G1, G2, and so on. And that's very obvious in all these numerical cases. Yeah, so here it's extremely obvious. Now for the non-renewal case, of course, I mean, the sums are like horrendous in a way looking, the G's, but they are closed form here. I mean, here there is, yeah, once one solves the eigenvalue problem, then yes, it's just a computer scientist can do that. And no numerical issues, it's just like a for loop and one gets the result.
Nice. Okay, thanks. Any other questions? All right. In that case, let's thank Florin one more time, and then I'll stop the recording. And if people have more questions, we can chat a bit after. Thanks again.